sorry. Yeah. All right, so let's get started. Internet unstable. Well, we'll see what happens. Okay, so what I want to do today is I want to finish off chapter 3. We actually don't have that much to do, so we'll do a little bit to finish off chapter 3. But then what we'll do is we'll focus on an example, and then if there's time, possibly a little demonstration. We'll see how that all works out. So one of the things that we ended with last time was this so-called projection operator. We were thinking of this in terms of like an analogy to like 3D unit vectors and stuff like that. But what we thought about was representing a basis, a set of eigenfunctions, a basis that spans our Hilbert space in this way. So we had a column times a row, which makes some kind of matrix. And when we put in for our Cartesian unit vectors, for example, what we showed is that if we summed over this projection operator, we actually produce the identity matrix. And so what I'd like to do is I'd like to do another more quantum version of that kind of calculation. So this is our projection operator p hat. And what I'd like to do is I'd like to take p hat and operate on a state EM. So this is just part of the EN eigenfunction set. It's just a different one. And we're going to assume that the different members of the set are orthogonal. So if we take the inner product with state N and state M, we get this delta function. Okay. So let's see what happens. We're going to take this projection operator and we're going to act on state EM. Well, the projection operator is this EN, and then we act on EM. But we just said we're going to assume this is a complete orthonormal set. So this is going to give us a delta function. If N and M are equal, we'll get 1. If they are not equal, we'll get 0. They'll be orthogonal. Okay, so what we have is this relationship. What I'm going to do next is I'm going to sum over all the members of this set of eigenfunctions. So I'm going to sum M equals, say, 0 to infinity for this complete set. Maybe if you like, you could have in mind something like the quantum harmonic oscillator, where we had states from n equals 0, 1, 2, 3, 4, up to infinity. Okay, so let's sum over all M. So what we're imagining is this p hat summed over all states M. Okay, but that's just going to be the sum of this thing. So that's the sum over M of delta NM. And our good friend, the Kronecker delta, is a killer of sums. What it's going to do is it's going to make non-zero only the term where N and M are equal to each other. And so this is EM. Okay, so that's kind of interesting. The sum of the projection operator acting on state EM returns EM. But if we think of this as like a column vector, what times a column vector returns the column vector? Well, it's just the identity. And so we could write this as the identity operator times this EM. So this is identity operator. If we think of EM as a column vector, then this identity operator would be the identity matrix. And so, of course, if we compare the left and right-hand sides of these equations, they have to be equal, obviously. They both multiply the same EM state. And so the only possibility is, therefore, that the sum of the projection operator which, remember, the way we define that was the following. That has to be equal to the identity operator. So that is one of the results that we're going to make use of today. All right. So this would be for like a discrete case where we have like a discrete set of eigenfunctions, such as in the quantum harmonic oscillator. But we've seen that we have other stationary states that are continuous, like the position and momentum states. And so for a continuous basis like position and momentum, the equivalent expression is that the integral of this combination of states with respect to z is equal to our identity operator, where most of the time z is just going to be labeling the basis we're working in. So z is usually going to be either position x or momentum p. So usually z would be x or p. And so essentially what I want to do for part of our remaining time is just to see how can we use this identity operator. What's it good for? So the identity operator can be used to express or let's say an abstract or a general quantum state let's say S in terms of components along a certain basis of eigenfunctions. And so it's not too difficult to see how this is going to work. What we'll do is we'll say, all right, if I take some general state, something that lives in Hilbert space, it's completely abstract. Well, I could always multiply that by the identity operator. And that's just going to return the state. But what we've seen is I can write the identity operator in these ways. So for example, let me take a discrete case for a particular example. It would be n, en, en, s. So this would be the discrete case. And the way to interpret this, the inner product just returns some complex number. And so this is like the coefficient. These are the coefficients, or if you like, it's the component. I'm gonna restart this app. It is lagging. This will be better, I think. All right, good. So here we go. So here are the coefficients, and this is our eigenstate. Okay, If, on the other hand, I had a continuous set of states, then we could just do the same thing. We would have our integral with respect to z, position or momentum, and we would have our eigenfunctions, and then we'd multiply by our general state. Okay, and so this is in the continuous case. Okay, so now these are just representations of our vector. And so what I could choose to do is I could say, I want to know how that vector is represented in position coordinates or momentum coordinates or something like that. So if I want, for example, the position space wave function psi of xt, it is given by, well, psi of xt is defined to be the inner product of the state, basis state x, with our general quantum state s. Okay, so that's fine, but as we've seen, I can expand s of t using this identity operator. So let's suppose I did it with x. So this would be x prime, and then we act on s of t. Well, if I compare these two, this x acting on s gives me the wave function. But here I have x prime acting on s, so I just get the wave function at x prime. Okay, so this is psi of x prime of t. And so what are we left with? So what I can do is I can say the wave function in terms of position coordinates, space coordinates, is x acting on s. Okay, so this is x acting on s, which is x acting on this thing. So we're going to get the integral of dx prime, and then I have x prime. So I act from the left with x. That comes inside the integral, acts on this thing, and then I have psi x prime t. But if x represents an orthonormal basis, then the inner product of x and x prime is going to be 0 if x prime is different than x, and it's going to be 1 if x is equal to x. And again, that's just the delta function. So this is delta x minus x prime. It's not the Kronecker delta. The Kronecker delta is for the discrete case sums. This is the continuous case where we have some continuous basis, some function of x. Okay, so therefore we can say psi of xt is equal to the integral of dx prime delta x minus x prime psi of x prime t. And of course, if you evaluated this integral, it would select the value x prime is equal to x, and we'd have consistency between the left and right. So we've kind of gone in a loop where we started with a general state, we expanded it in terms of our a chosen basis set of basis states x, and if I want the x representation, we just say get this result. I like this. This is kind of, in some sense, it's a bit like how the collapse of the wave function is sort of built into the theory. Before I make a measurement, I don't know where my particle is. It could be at any range of x values. And the probabilities are given by this guy. So I get different probabilities for different x primes. So the wave function is really just a continuous list of probabilities of finding the particle at some position. I should say probability amplitude, because we have to take the absolute square to get the probability. So it's the probability amplitude. And it's not until we make the measurement and we select a specific value for x prime that this collapses into a specific state at a specific position. Okay, now that's fine, but I didn't have to choose to expand my system in terms of x eigenstates. I could have made a different choice. So we could have said, however, we could equally well express our quantum state in terms of a different set of eigenfunctions, or in other words, a different basis. Maybe I want to express it in terms of the momentum basis. Well, I would do the exact same approach. I'm going to multiply S by the identity operator, but I'm going to express that identity operator in terms of the momentum eigenfunctions. And so it'll look something like this. But just like we said, X projected onto S gives us our wave functions in the X representation. P projected onto S gives us our wave functions expressed in terms of momentum. So this is the momentum space wave function. Okay. So I'll just write it out again. S of t is equal to the integral of, let's say, dp, the momentum space wave function, and then we still have p, the eigenstate left over. So we're summing over all eigenstates again. It's a continuous sum, and this is like the probability amplitude for being in each state of a particular momentum. All right, good. So now, again, if I want psi of xt, what I would do is I would just evaluate the inner product between x and our general quantum state. But now I'm going to use x in terms of the momentum basis. And so what's that going to look like? It'll be this integral of dp, the momentum wave function, and then we have our eigenstate. And so we bring the x inside, it's going to act on this p. So we have the integral dp phi of p dt, and then we have x inner product with the momentum eigenstates. But we've worked this out before. These are the momentum eigenstates in the position or x representation And if you look back in our notes, we worked this out. It was 1 over 2 pi h bar e to the I px over h bar. Right. Sorry, I don't need the dp. The dp is part of the integral already. Okay. So what we're going to do is we're just going to set that into the integral and see what we get. And so therefore, psi of xt is going to be, let's see, we have a 1 over 2 pi h bar. And then we have an integral with respect to momentum. Then I'll write my phi of p, phi p of t, our momentum space wave function. And then we have our exponential factor. Okay, so this is e to the I px over h bar. And that's it. And we've seen this before. This is exactly the Fourier transform. Or it's the inverse Fourier transform. So we go from a function of momentum to a function of position. And so this is exactly the inverse Fourier transform from momentum to position. And so there's this internal consistency with our new formalism that gives us results that we've seen before. So what I want to do is I want to just highlight the fact that we've got different but equivalent ways of representing the exact same wave function. So here's our wave function in units of position expressed in terms of position eigenstates. And so here is our wave function in units of position, but expressed in terms of momentum eigenstates. We're going to do one more. So for a discrete basis, we would say S. I'm going to multiply it by the identity operator again, but this time for my identity operator, we'll just use some discrete eigenstates. Again, I like to think of the harmonic oscillator, for example, and we're going to act on our general state S. This is our Cn coefficients. So in fact, maybe we'll write it as Cn as a function of time. And so it is some complex number Cn. If we square that complex number, it tells us the probability of being in state n. And then the time evolution was from our separation of variables a long time ago. And it had this exponential factor e to the minus I e n with t and h bar. Okay. So that means if I wanted to, I could, again, construct my wave function in terms of position variables. And to do that, I'm just going to act on this thing. And so it's going to be equal to, let's see, there's going to be a sum over n. We've got our Cn. And then we have e to the minus I e n t over h bar. And then we have x acting on, sorry, it's en. I should write en. But if this is something like the quantum harmonic oscillator, then we know that the states in terms of variable x are like the Hermite polynomials with the e to the minus z squared over 2 factor. We work those out. And this is exactly what they are. This is psi n of x. This is the position representation of our energy eigenstates. We called them stationary states when we were working them out the first time. Okay, and so that means our wave function written in terms of x is sum over n Cn e to the minus I E n t over h bar psi n of x. And so there are 3 distinct but equivalent ways of representing the exact same wave function. And the difference is just, is it expressed in terms of energy eigenstates? Or, so let's say 3. Or is it expressed in terms of momentum eigenstates? Or is it expressed in terms of position eigenstates? So let's say 1, 2, and 3 express the same wave function in position coordinates, but as components of different eigenstates. Either it could be eigenstates of the position operator or the momentum operator or the Hamiltonian, the energy operator. All right, good. So that's the wrap up of the conclusion of chapter 3. So what I want to do is I'd like to try to implement some of these ideas in a concrete example problem. So we're going to work through example 3.8 of Griffiths. Okay, and so we're going to consider a system with a discrete number of eigenstates. And to make this simple, we're going to have only 2 states. He doesn't mention this, but really what we're kind of building up towards is a lot of this formalism that we'll work through right now is directly applicable to spin. So electron has this quantum spin, and if you put it in a magnetic field, it either aligns parallel or anti-parallel with that applied magnetic field. And so those are the 2 states. So if you like, you can think of these 2 states as spin up, parallel with the applied field, or spin down, anti-parallel. So let's consider a system with just 2 states. So it's a discrete system. I can write down the 2 states explicitly. We'll call state 1, 1, 0. Okay, so it's like a little vector. And if you want, you could have in your back of your mind, this is like the spin up state. And we have our state 2, let's say, we'll call it 0, 1. And this would be, if you like, the spin down state. These are already normalized, right? If I take the inner product of either of these states with itself, you can confirm that you'll get 1. It's just a little matrix multiplication. If I take the inner product between 1 and 2, I'll get a 0. So they're also they're not only normalized, they're orthogonal. So they're orthonormal. All right. So the most general state I can make out of a superposition of these 2 is just some A times state 1 plus B times state 2. Okay, so the most general quantum state in terms of these eigenstates is, so some general state is A times state 1 plus B times state 2. But state 1 is just 1, 0. So A times 1, 0 is A0. And state 2 times 0, 1 is 0 times, so state 2 times B is B times 0, 1, which is 0 over B. So we have A over 0 and 0 over B. If we add them up, we just get A, B. All right. So let's normalize this. We require the inner product of S with itself has to be equal to 1. But expressed as an explicit vector like this, the raw part of the inner product is going to be the transpose and conjugate of S. And then the ket part is just the state itself. And if we multiply this out, it's A star times A, which is A squared. And B star times B is the absolute square of B. And so we need this to be equal to 1 for normalization. All right, so let's just keep that in mind. Now, what we're going to assume is that these states 1 and 0 are going to be, we would like to operate with the Hamiltonian on these states and find out the energy. Okay, so the Hamiltonian H hat can be represented by a matrix. In fact, it's a square matrix. Okay, and the way we do that is we say, look, the mnth element of our Hamiltonian matrix is going to be given by state M acting on H times state N acting on H. So let's just work out some of these matrix elements. If we want the element 1, 1, what we'll do is we'll act with state 1 on H times state 1, like so. Okay, now we don't know ahead of time what this is going to be, but this is just an expectation value. And so it's just going to be some number, and I'm just going to call that H, because I don't know what it is yet. It's the expectation value for the energy of state 1. So this is the expectation value of the energy for state 1. And so we might call that E1 or something like that. So H is like E1. And then we keep going and we say, okay, if I wanted the 1, 2 element, row 1, column 2, I would do 1 H hat 2. And again, we don't know what that is, so we'll just call it G. H21 is going to be 2 H1. I'm going to call that J, and then we have the H22. And that has to be K. We'll just define that. So what we've done is we've constructed this matrix like so. So where really the way I think of this is when we represent our operators as matrices, it's like we've pre-computed all the expectation values. Okay. Now, what I want to say about this is that actually the Hamiltonian matrix is restricted more than what we've shown. The reason it's restricted is because, remember, we proved that operators of physical observables, of which energy is something we can measure, they have to be Hermitian. So recall that operators representing physical observables have to be Hermitian. And so specifically, it was like this adjoint of H has to be equal to itself. What that meant in the matrix representation is that the transpose and complex conjugate of H has to be equal to itself. So if we enforce that, it actually reduces how many independent elements we have in this matrix. So H is, we said HGJK is the most general possibility, except for the fact that if I transpose, I'm going to get HJGK. And then if I take the conjugate, complex conjugate, I'm going to have to take the complex conjugate of all these. And so these have to be equal. And right away, we can see some things that happen here. H has to be equal to H star. Well, the only way that a complex number is equal to its complex conjugate is if that number is actually real. So we see from this that H is equal to H star. That means H is real. Likewise, K is equal to K star. That means K is real. All right. Well, the other restriction we see here is that J is equal to G conjugate and G is equal to J conjugate. So that gives the same bit of information. J and G are the complex conjugates of one another. So the other thing we know is that J is equal to G star, or equivalently, J star is equal to G. Okay, so therefore, after enforcing H at a joint is equal to H. So after enforcing that our operator is Hermitian, the most general Hamiltonian matrix is, well, okay, so H is equal to H, K at G and G star. So I replace J with G star. And then we have to know that H and K have to be real. All right. So that's just a little extra thing that I put in there just to remind ourselves of some of the stuff we've been thinking about. What Griffiths does in this example problem is he chooses an even more simple Hamiltonian. So for even more simplicity, for this problem, we assume that what are we going to do? We're going to assume that G is real. So G is equal to G star. And we're going to assume that H is equal to K. All right. Remember, the H represented the expectation value of the energy of that first state. It's like the E1. And then the K would be the expectation value of the energy for the second state. It's like E2. So when we say H is equal to K, what we're assuming is that if we're thinking of this as a spin, whether we're spin up or spin down doesn't change the energy. And then there's some off-diagonal elements. Those off-diagonal elements would come from the potential. So what we're going to work with is we're going to assume that H is equal to H, and then G. Okay, so the diagonal elements are the energies, say E1 and E2 of the isolated states 1 and 2. When we get off-diagonal elements, it's from the potential. Now, we haven't specified our Hamiltonian. We haven't written down like some differential equation for our Hamiltonian that has two derivatives of x for the kinetic energy plus the potential. But it would be the potential that is going to create these off-diagonal elements. The off-diagonal elements are determined by the potential V. And so we don't know what that potential is, but it could be some interaction between the two states. Okay, so now that's the setup. And so what we're going to do is we're going to suppose at t equals 0, we start in state 1. Okay, so somebody has arranged the system for us and they said, okay, here you go, I'm going to start a stopwatch. I've set up your system, so you're in state 1. And the question is, what is the state of the system at some later time? Okay, so what we'll do is we'll start. Okay, let's write down, first of all, the time-dependent Schrodinger equation. I h bar d by dt acting on state s, which is a function of time, is equal to our Hamiltonian acting on that same state. So what we'll do is we imagine we've done some separation of variables, and we're going to start with the time independent Schrodinger equation. And so we're going to be looking, so remember how we got to the time independent Schrodinger equation is we did a separation of variables so that we could get a differential equation just in terms of position. And then we got a different one for time, which actually turned out to be easy to solve. It was e to the minus I e t over h bar. So when we do the time independent Schrodinger equation, we're not looking for the t dependence, we're looking for the dependence of, say, something like x or something like that. So that is, I'll write this as little s without any t times e, which originally, remember, was our separation of variable constant. We now know it's the energy. Okay. So, well, the time-independent Schrodinger equation. We write down our assumed Hamiltonian in matrix form, and we take some general state. I'll choose x, y, and we're going to try to find x and y that satisfies this time-independent Schrodinger equation. So this is equation 1. This is our eigenvalue equation, our eigenequation, if you like. So the goal is to find x and y that satisfies the time-independent Schrodinger equation. Now, I assume that you've all taken a linear algebra course where you've learned how to solve eigenvalue equations. Is that correct? You've seen it? Yeah. So I'm not going to rederive everything from scratch, but I'll go through this example slowly to remind you of the process. Okay, so this is now linear algebra. All right, so what I'm going to do is I want to make this look like I want to have square matrices on both sides. And so to do that, I'm going to multiply, or I'm going to insert the identity matrix here. So we could write this as HG, GH, XY, nothing changes there. And I'm just going to put in an E, and then I'll put the, I don't know, identity matrix times our state XY. All right, fair enough. So HGGHXY, and I'll actually write out the identity matrix 1, 0, 0, 1, XY. All right. So what I'm going to do is I want to have an expression that is equal to 1. Equal to 0. So I'm going to take all of this stuff and I'm going to subtract it off. So we'll get HGGHXY minus. Okay, so I'll multiply through the E. So we get E0, 0, E XY is equal to 0. All right. And so I can combine these two matrices. They multiply the same vector, the same column. So we could write this as, let's see, H minus E, G, G, H minus E, all multiplying XY is equal to 0. All right, so that's the setup. Now, once you're comfortable with this, what you would do is you would go from here immediately to here. All right. What do we require in order for X and Y to have a non-trivial solution? Yeah. Yeah, that's right. So the reason that, let me remind you, the reason the determinant has to be equal to 0 is because if the determinant is equal to 0, then we cannot invert this matrix. And so I can't multiply by the inverse on both sides, which if I could, then I could prove that XY could only be equal to 0. So if the determinant doesn't exist, that means there must be some other solution XY that satisfies this equation. Okay, so the solutions for E, which are our eigenvalues, are found by requiring that this determinant, so HE, G, G, H minus E has to be equal to 0. All right, so we have a 2 by 2 matrix. The determinant is easy to calculate, and this diagonal minus that diagonal. So therefore, we have h minus e squared minus g squared is equal to 0. All right, so that means, let's see, h minus e is equal to plus or minus g. So we could sort of bring the g to the other side, take the square root, and then we get a plus minus. Well, that means there's two solutions for e. One of the solutions is, let's say e plus is going to be equal to, let's say h plus g, and e minus is equal to h minus g. Okay, good. Those are our two eigenvalues. And I want you to notice something. What we said is that h, that's where the hell is h? Way the hell back here. Where did it go? Here it is. H is the expectation value of the energy for state 1. And then we ultimately ended up saying, let's make k equal to h as well. So what we assumed from the beginning is that the energy of the two isolated states were equal to one another. And then we decided that these off-diagonal elements were a result of some kind of potential, some interaction between the two states. And we set them equal to g. And so we end up getting something kind of interesting. So let's recall that h, it was the expectation value for E1 and E2, right? And so we said E1 is equal to E2 is equal to H, and this was for isolated states, non-interacting states, if you like. And then G were the off-diagonal elements, and it seems like when we include the potential that has these states talk to each other in some way, communicate, then we get a splitting of that energy. And that splitting is determined by G. Specifically, if I take delta E is equal to E plus minus E minus, that's equal to 2G. And this is like the energy splitting due to an interaction between the states 1 and 2 via the potential, if you like, off diagonal matrix elements. Okay, so let's just keep that in mind. Now, what I'd like to do next is I'd like to go back, and we have the eigenvalues. We should be able to now reconstruct the eigenvectors. Okay, so now that we have the eigenvalues, so E plus minus is equal to H plus minus G. What we can do is, did I write down in equation 1? Yeah, I did. So we have equation 1. I'm going to sub those eigenvalues back into equation 1 for E, and we're going to try to solve for x and y, the eigenvectors. Now that we have the eigenvalues, we can sub them back into 1 and find the corresponding eigenvectors. All right. So from 1, let's see. Maybe I'll rewrite 1 so we have it in front of us. It was HGGH xy is equal to EXY. That's our eigenvalue equation. All right. So therefore, I'm just going to do some multiplication. H times x plus g times y is equal to E times x. All right. So hx plus gy is equal to EX. And what's the other one? Gx hy is equal to EY. So gx plus hy is equal to EX. Sorry, it must be y. I got it written down wrong there. Okay. So I'm going to call this, say, 2 and 3, because we already have equation 1. So from 2 with E equal E plus, what are we going to get? So hx plus gy is equal to E plus. E plus is h plus g. And then we multiply by x. And let's see, we have hx on both sides, so I can cancel those. And so I have gy is equal to gx. I can cancel those. And so therefore we get y is equal to x. Now, I'll leave it to you to confirm, but if we did the same thing with equation 3 using E plus, we get the exact same relationship. There's no new information. So we get the same results using 3 and E plus. So all we can deduce is that x is equal to y. We can't figure out the absolute value. The reason is because once we pick x equals y, we could pick that arbitrarily. We're going to pick x and y equals 1. Or let's say capital A, let's say. And then we're going to set the value of A through normalization. So we can arbitrarily set x equal to y equal to A. And so our eigenfunction is, let's say, well, our eigenfunction is going to be A, that's a stupid way to write it, A11, and it has eigenvalue E plus is H plus G. Okay. Normalization requires that A squared times 1 times 1 is equal to 1. And so let's see, 1 times 1 plus 1 times 1 is 2. And so A is 1 over root 2. And so our eigenfunction, let's say S plus is equal to 1 over root 2 A times 1. So that's our S plus eigenfunction with eigenvalue E plus. Okay, so let's do S minus and E minus. Okay, so from equation 2, we have, well, let's remind ourselves, what was equation 2? hx plus gy is ex, but we're going to put in e minus there. So hx plus gy, hx plus gy was equal to e minus, which is h minus g, and then it's times x, right? Yes. All right. Well, a lot of the same stuff happens. We still have hx on both sides, and so those still cancel. And so we end up with gy is equal to minus gx, and the g's cancel. And so now we get y is equal to minus x, and we arbitrarily set x is equal to minus y is equal to a. Okay, so that means our eigenstate is going to be a. What's going on? A 1 minus 1. And normalization requires that this inner product is 1. So we'll get the absolute value of a squared. Then we get 1 minus 1. 1 minus 1 is equal to a squared. Well, 1 times 1 is 1, and then we go plus minus 1 times minus 1 is again plus 1, so we get 2 again. And so therefore a is again equal to 1 over root 2, and our S minus eigenstate is 1 over root 2, 1 minus 1, with eigenvalue E minus is H minus G. Okay, so that is the solution to the time-independent Schrodinger equation. That's where the hard work is. Now, we've done a simple case, but if we had a more complicated Hamiltonian, maybe 3 by 3 or whatever, the process is the same. Maybe finding the determinant is more work. Maybe solving the eigenvalue equations and the eigenfunctions is more work, but the procedure is the same. Okay, so finally, we can actually answer the question they asked. And the question they asked is, what is the time dependence? What's the time evolution of this quantum state? So we were told at t equals 0, the state was 1, 0. That's what we were told. Now, if we look at S minus, where's S plus? And S plus, let's imagine we took the sum of those twos. So if I took S plus S minus, I'm going to get a 1 plus 1 is 2. And then I'm going to get a 1 minus 1 is 0. And so that's pretty close to what we were looking for. In fact, if we write this as 1 over root 2 times S plus S minus, that is exactly our original state, because these each have a 1 over root 2 factor. So times by this 1 over root 2 gives a 1/2. It's going to kill the 2 that we get in the first upper element. And so we'll get a 1, 0. Okay, now we don't have to do anything new to find the time evolution of this state. It's all of that separation of variable stuff that we did. It is equal to 1 over root 2. And then we have a factor of e to the minus I e plus t over h bar times s plus e to the minus I e minus t over h bar s minus. Okay, well, let's keep going. 1 over root 2. Let's see. E plus was e to the minus I. So e plus was g plus h. So I'll write the h first. T over h bar. E to the minus I g t over h bar s plus e to the minus I. Now e minus is h minus g. So we get an h t over h bar e to the, this time we get a plus I because we had a minus g in our e minus. So we get a g t over h bar s minus. All right. So we're getting pretty close to what I wanted to get to. And we probably will have time for that quick demo. Let's see. There's a common factor. This first exponential is common, so I'm going to take it out. So st is equal to, let's see, e to the minus I h t over h bar 1 over root 2. And then for the s plus, I'm going to put in our column vector, e to the minus I g t over h bar 1 1 was our s plus state. And let's see, I guess it probably has a factor of root 2 as well, doesn't it? And then we get plus e to the plus I g t, that's not a t, t over h bar 1 minus 1, and it also had a factor of root 2. Okay, so e minus I h bar. God, I'm so used to writing h bar that I can't write a regular h. H t over h bar. Okay. 2. So I'll take out this root 2 here. Now let's combine these two. 1 plus 1. So that's going to be an e to the minus some exponential, e to the plus some exponential with an I. That's like the cosine. So this is going to be, in fact, I can do it like this. 2 cos g t over h bar. And let's see, here I have the difference. So it's e to the minus I some stuff minus e to the plus I some stuff. That is minus 2I sine g t over h bar. All right. So finally then, s of t is equal to, let's see, we'll cancel the 2's here. It's going to be e to the minus I, oh, I did it again, by h bar, I, 8, oh, I did it again. Okay, minus I, h, t over h bar. All right, and then we just have our cosine factor, cos g t over h bar, and our sine is minus I sine g t over h bar. Okay, and so that's the solution, and I want to think about what it means. What the solution suggests is, let's imagine we can find a time, these cosine signs have the same arguments. So, for example, when t equals 0, I'll get cos of 0 is 1. When t equals 0, I'll get sine of 0 is 0. So I'll get 1, 0. That's our initial state. So at least it does correspond to our initial state. But when this combination is equal to pi by 2, I'll be in 0, 1, or 0 minus I. When I'm at pi, I'll be in -1, 0. When I'm at 3 pi by 2, I'll get plus I and 0, 0 and plus I. So I'm alternating between being in state 1 and state 2. And I alternate through those periodically, and the frequency is determined by G over H bar. So S of t oscillates between states 1 and 2, state 2, 0, 1, periodically, and the oscillation frequency is given by omega is G over H bar. But remember, we said G, where was it? G. There it is. G is just the energy splitting, or it's 2 times the energy. So it's delta E over 2, which is equal to delta E over 2 H bar. So the takeaway is that the interaction between our states 1 and 2 via the potential leads to, okay, 1 is an energy splitting, and 2 is an oscillation between the 2 states with omega is 2 delta E over 2 H bar. These are called Rabi oscillations. So this demo that I've been talking about is to show you that Rabi oscillations is not a quantum phenomenon. That's a classical phenomenon. We're just seeing it play out in a quantum system. And so I've got a demo here. I'll go a couple minutes over, but it's going to be worth it. Okay, some of you may have seen this already, but probably not in this context. So what I have here is a pendulum. This pendulum, it can oscillate up and down. It has a translational mode of motion, but it can also rotate. It has a rotational mode of oscillation. These 2 modes of oscillation are coupled to one another. They're coupled because when I stretch the spring, it naturally causes it to kind of twist. Alternatively, if I twist the spring, it will naturally either lift up or down. And so that's the coupling between these 2 modes. And so I want you to think in terms like this. Our little quantum system here has 2 modes, 2 eigenstates. They're coupled through the potential. My little oscillator has 2 modes. They're coupled through the spring. So the spring provides that potential, doesn't it? The delta E is the splitting in energy. So what I'm going to get here is not a splitting in energy, but a splitting in the oscillation frequency. So we started with our 2 isolated states in this quantum system. They had the same energy, right? That was the 2 diagonal elements of our matrix. Where the hell did it go? HH. 2 isolated states of the same energy. So for this demonstration to work, I need to make it so this translational oscillation is the same frequency as the rotational one when there's no coupling between the 2 modes. And so that's why these little bars are on a threaded rod, because I can move them in or out when I move them in or out, I change the rotational inertia of the rotational oscillation. And so I can tune that to match it to the horizontal one. And so what we should expect to see is our system, our little oscillator, should periodically oscillate between being in the rotational state and the translational state. And so let's see what happens. So I'm going to start this oscillating. Okay, and so what we're going to look for is eventually the translational oscillation should die out completely. And so it's approximately done that. And what will happen is the rotational one will start to die and the oscillations will grow. The oscillations translation is growing now, and those rotational modes die out. Then the translational one will start getting smaller, and this will start rotating more and more and more. And the frequency or the time it takes to switch from the oscillating mode translation and the rotational mode is determined by the energy splitting delta E, which is how strongly are the two modes coupled. So let me see if I can do this a little better. Freaking arm's getting tired. Okay, so I'm going to throw this thing down. So we started in translational, and it should evolve into purely rotational. And then, so that's about now. And so this rotational one will start dying out, and the translational one will start growing. And this will just keep going and going and going until this is damped. So we're losing energy as we go. But if there was no damping, it would just continuously oscillate between those two modes indefinitely. And that's what we just calculated for our quantum system. But this effect of Rabi oscillations is a classical effect for waves, for wave phenomena. The quantum stuff is in finding the eigenmodes and the eigenvalues and all that stuff. All right, so that's it. Thank you very much. Have a good couple of days. We're going to start chapter 4 on next week on Monday.